All right, so we're continuing on talking about regression. And in this video, we're going to be talking about the sampling variation of ordinary least squares. So we're going to set to the one side our whole issue with causal identification for a second, and we're just going to be talking about how sampling variation can really mess us up, right? We're dealing with statistics here. When we are estimating some sort of model or some sort of coefficient or whatever it is, we are at the mercy of the fact that we do not have all the universe's data. And so we need to deal with that fact by recognizing that there's going to be variation in our estimate that simply has to do with the data set that we happened to get when we sampled some data. We know that the estimate we get is not a perfect representation of the truth, but it is a representation of that truth, ideally, if we've done our job right, but then also has some sampling variation and noise built into it. Let's talk about what that is. So what we are interested in understanding is we have done a regression. We have estimated our regression model. We have gotten a coefficient on a variable, and we want to know, what does that estimate actually mean? Now, conveniently, we know quite a bit about the sampling variation of an ordinary least squares coefficient. I'm not going to do the proof here, but you can show very easily that an ordinary least squares coefficient follows a normal distribution across samples, which means that if you gathered some data, estimated an ordinary least squares coefficient, and then gathered some different data and did the same thing, and then gathered some different data and did the same thing, and on and on and on and on and on and on and on, and you look at the distribution of the estimates that you got across all your different samples, it would follow a nice normal distribution. Further, conveniently, we also know about the center of that normal distribution. The normal distribution would have a mean of the population parameter, by which I mean if you did, in fact, have all of the data in the universe and you estimated your model, then the parameter that you get would also be the mean of the sampling distribution. So on average, ordinary least squares gives you the population parameter, which by itself, note, is not necessarily the actual estimate that you want. That population parameter could be biased if you have not got causal identification, but like I said, that's for later videos. The important thing is we get a normal distribution. That normal distribution is centered at the population parameter, which is nice because it means that we can use that distribution idea to learn some things about what we think the population parameter is based on the single estimate that we happened to get. I should be able to say things like, well, okay, let's say I got an estimate of 2.5. Now, I don't necessarily know what the population parameter is. If I had all the data in the world, maybe I would get 2.5. Maybe I'd get 3. Maybe I'd get 2. Whatever it is. But I should be able to say something like, well, if I got 2.5, then the truth is probably not that it's 10, right? I can make claims like that. These sorts of claims are made easier by the fact that we also know quite a bit about the standard deviation of that sampling distribution. If I gathered all those samples and estimated my OLS coefficient again and again and again, I would get a distribution of estimates across all the different samples. And that would be normal, it'd be centered at the population, and also the width of that distribution, the standard deviation of that sampling distribution, which is, by the way, called a standard error. That's what a standard error is. It is a standard deviation of a sampling distribution. The standard deviation of that sampling distribution can be calculated as this. So here's the standard error of an ordinary least squares coefficient. And what do we have here? There are three main components that go into our standard deviation. And these become easier to think about if you realize that the standard deviation is talking about the precision of our estimate. How much can we actually say about this parameter based on the estimate that we have? The more information we have, the more we can say. The more we have, the more leverage we have. So that's where these three terms come from. So what do we have here? So first, up here in the we have a fraction. Up here in the numerator, we have sigma. Sigma is basically the prediction error of our model. You can sort of think of it as being the sum of squared residuals that we still have left. It's the variance of the error term, which we estimate using the variance of the residuals. This is basically representing how closely our model is capable of predicting the outcome. If we have a model that we can use to very accurately predict the outcome, well, that means that we know a whole lot about what's going on. And if we know a whole lot about what's going on, then we can say what we think our parameter is with a great deal of confidence, with a fair amount of precision there. So if the residuals are quite small, then this term will be quite small, and our standard deviation will be quite small, which means our standard error will be quite small, and we'll be able to say with quite a lot of confidence and precision what we think our estimate is. If we know a lot about the outcome, then simply our estimate of the coefficients is not going to vary that much from sample to sample. So that's one thing that goes into our standard error calculation, the precision of the model, how much predictive power our model has. The second term that we see in the denominator is the variance of x. So what's going on here is that we basically can say more about a variable's effect if it moves around a lot. And the reason for this is quite intuitive. If you see a variable moving around quite a bit, then it will be very easy to see whether the outcome is also moving around at the same time, right? If this is moving around a lot and y is basically staying still, then you know that, yeah, there's nothing happening there, right? But what if x is just moving around a tiny little bit and you don't see y changing much? Well, maybe it's just that we can't see it because there's not that much movement going on. Whereas the more movement that you have along the x-axis, the easier it is to see if there's also movement along the y-axis. It's simply hard to study things with statistics that don't have much variation in them. So the more variation we have in our x, the more we can say about the relationship between x and y, simply because there's a lot more differences to look at. It's a lot easier to see if this thing is having any sort of effect at all. So the more variation we have in x, the more we can say about the effect of x, because it'll be pretty easy to notice if there's not anything going along with x. The last thing that we see here in the denominator as well is the sample size n. And this one's pretty easy. The more observations we have, the more information we have about our ordinary least squares estimate, and therefore the more precision we will be able to have in what we are saying about it. So the standard error will be quite small with a large sample because we simply have a lot of information to build our inferences off of. So there we have it. We have a sampling distribution for ordinary least squares. If we gather a bunch of samples and we estimate ordinary least squares in each one of them, we know that the result that we get will have a normal distribution with the center at the population parameter and a standard deviation that is based on how much of our model, how predictive our model is, how much variance there is in the predictor, and then also how much of a sample size we have. Why are we bothering to do this? Why are we focusing so much on trying to understand the sampling distribution? In fact, in general, why do statisticians care so much about distributions and trying to figure out whether different variables fit different distributions? Well, the reason why is that once you have a theoretical distribution that explains how a thing varies, that gives you a lot of power in explaining what the truth is, what those population parameters are. If I've estimated an OLS coefficient of, let's say, 2, then it's quite unlikely that came from a distribution where the population parameter was 100 and the standard deviation was 1, right? If that's the sampling distribution, we will pretty much never, ever, ever see a value as low as 2. And yet we did, and so therefore that tells us something. It tells us that this is the wrong sampling distribution, which brings us to the concept of hypothesis testing. Now, I'm not going to go super duper deep into hypothesis testing. If you've taken any sort of statistics class, you've probably already done quite a bit of it. But let me tell you about how I think about it, especially in the context of regression. And I especially want to talk about it here because I think hypothesis testing is something that people get wrong a lot. Even if they've learned about it before, it's a very nuanced kind of thing, and it's very easy to interpret things in the wrong way. Here's what hypothesis testing is. You start with an assumption, right? We're going to make an assumption about the world, and that is going to be our null hypothesis. A null hypothesis is an assumption about the world that we are making, and we're going to now evaluate. So let's say that I'm making an assumption that the true population parameter of my OLS coefficient is 100. Then, once we have our assumption, we will try to build a sampling distribution based on that assumption. And since we know the theoretical distribution of an ordinary least squares coefficient is normal, with a mean at the population parameter and a certain standard deviation, I can use those 3 facts to say, okay, well, if I'm assuming something about the population mean, well then I know that it's normal, I know that it has a certain standard deviation, and so I know exactly what the sampling distribution would be. I know that if my assumption was correct, if my null hypothesis was correct, I can tell you exactly what the sampling distribution would be, and how likely it might be to get any particular estimate under that sampling distribution. We have a sampling distribution that tells us how likely or unlikely different outcomes are to occur given that distribution, right? And we also have an outcome, an actual estimate that we have created from the single sample that we happened to draw. Now, what happens if this outcome was very unlikely to have occurred from this sampling distribution, right? So, for example, let's say we have a distribution of heights, right? We just get average people, we get a bunch of people's heights and we estimate their average height. We say, I think my null hypothesis is that the average person's height is 5 feet and 7 inches. All right, that's my hypothesis. That's the average height. I can use that hypothesis, that null hypothesis, to say, okay, well, if that's true, then if I get a sample of people, then I'm going to get some sampling variation, and I'll get a sampling distribution. It'll be centered around that 5'7" amount. But so, sometimes I'll be above, sometimes I'll be below. It'll vary from sample to sample. But now let's say that I get a sample of people, and this sample of people happens to be 3 feet tall, right, on average. Well, that is very unlikely to be a result that I would get just from random chance. If indeed the average was 5'7", and I just randomly picked some people, it's very, very unlikely that I would find that my average had a height of 3 feet tall. So, what can I infer from that? Either, I have basically two sort of contradictory things. I have this outcome that is very unlikely to have occurred under the null hypothesis. And so one of two things happened. Either something very unlikely just occurred, or the assumption that I made in the first place to build this null hypothesis is incorrect. That is what hypothesis testing is all about. We are using an assumption to build a sampling distribution. That sampling distribution will tell us how unlikely our outcome is to have occurred. And then we have to make a choice. Do we think that something this unlikely actually happened? Or was our assumption wrong in the first place? That is all that null hypothesis testing is. It is not telling you how likely it is that the outcome you did get is correct. It doesn't tell you that. All that it tells you is that the assumption that you made in the start that built that sampling distribution, whether that is unlikely to still be true, right? Whether you have evidence that suggests that, if that thing that you assumed was true, then we probably wouldn't have ended up where we did. And so we did end up where we did, so maybe that wasn't true in the first place. Now, there are a lot of specifics in doing a null hypothesis significance test that I've left out. For example, calculating the probability that we got the outcome or something even weirder than the outcome given that sampling distribution. That's called a p-value. That's the probability that we saw a result that far from our null, roughly. I'm trimming words a little bit here. Or even weirder. So, for example, if we think that our null hypothesis value is a height of 5'7", and we got a height of 3 feet, then that's asking what's the probability that given this sampling distribution, we would get a result that's 3 feet or lower, or perhaps even that's similarly weird but in the other direction. That's a p-value. We might then choose a cutoff. We might say that if the p-value is below some certain cutoff, then we will now reject the null hypothesis, and otherwise we will choose not to reject it. The logic there is, if let's say there's a less than 5% chance that this outcome came from this sampling distribution, then the trade-off of, maybe something weird just happened, or maybe the assumption was wrong, is going to now tilt in favor of the assumption was wrong. Whereas if it was likely enough to happen, maybe with a p-value of 0.25, where this sampling distribution could produce something like that 25% of the time, we'd say, yeah, I know that's still not that likely, but it's not so unlikely that I'm going to reject the assumption that I started with. That's what p-values and choosing a cutoff and significance testing is actually about. Now, to close things out, I do want to say significance testing is probably a little bit over-applied. It's a very useful concept, but there are a lot of things that can go wrong with it, and especially in the ways that people interpret it and get it wrong. And so I'm going to keep using significance testing in this book because it's just simply so common. And it is, I think, a good tool for thinking about sampling variation. But you don't want to take it too seriously. And what do I mean by that? First of all, something that you want to recognize when you're doing hypothesis testing is that the null value that you chose is probably pretty arbitrary, right? Generally, when you're doing a hypothesis test, the most common null hypothesis value that you're choosing is 0. You're saying, can I reject the sampling distribution that comes from an assumption that this OLS coefficient is 0? Well, often that's not really that interesting of a question. If we're talking about social science, pretty much all relationships are non-zero, at least a little bit. And so rejecting a null of 0 is sort of rejecting an assumption that nobody expected to be true in the first place. So like, big whoop that it's not 0. That's not that important. Also, you really have to ask, well, what are the nulls that you are not rejecting? Like, sure, I can reject 0, but can I also reject 0.01, 0.02, 0.03? If I did find that it was in truth 0.03, would that still be something that I would say, oh yeah, well, at least it's not 0? For that, you might want to think about, instead of doing a sharp hypothesis test, doing something like a confidence interval that shows you the range of nulls that you can't reject. That's a different question entirely. So null hypothesis significance testing is very sensitive to the null that you choose. The other thing about significance testing is that we tend to interpret it as being like, okay, well, if I found a significant effect, there's an effect there, and if I didn't, then there's not. But keep in mind, there's a lot that goes into a significance testing result other than just, is there actually a true effect or not? It includes things like your sample size and other determinants of the precision of your estimate. There are lots of effects that would be statistically significant with a large sample size that are not significant with a small sample size. The true effect didn't change there, just the sample size did. So it's more about whether you have evidence to show that that null is wrong rather than the null actually truly being wrong or not. And that's in addition to other things like sampling variation and also how you construct your model. Speaking of constructing your model, we tend to have this weird idea that significance, getting a statistically significant result is like a good thing or a success. We even reflect that in terms like we got a positive result. But that's not really right either, right? If the truth is that there isn't an effect there, then that's what you want to find. Finding an insignificant result when there's not really an effect to speak of is a success. That's what you wanted to find. You wanted to find the truth. And yet, because we think of getting a statistically significant result as a success, we will tend to chase that success. We will change our models so that they will be statistically significant, whereas they might not have been before, which I want to really super duper emphasize. Don't do that. If your result is statistically insignificant, do not change it so that you get a statistically significant result, please, I'm begging you. Statistics professors always tell you not to do this, and then everyone remembers the opposite. I don't understand why. I mean, I kind of do understand why, but also please don't do it. For a couple reasons. One, it makes the test wrong. If you got a p-value of, I don't know, 0.15 before, and then you change the model and you got 0.04, and you're like, oh, it's less than 0.05, and that was my cutoff value, it's statistically significant, that doesn't actually mean that you found statistical significance, because all the tests, all those calculations, are working under the assumption that you didn't do the thing that you just did. So your calculation of your p-value is wrong. You might not even be statistically significant at the level that you've chosen. Also, there's a lot of choices that go into doing these sorts of tests, and if you try enough of them, you will find a way to make your results statistically significant. And remember, those different choices that you're making in your analysis aren't changing the truth, and yet they're changing your results. You don't want that to be the case. You want to reflect the truth. You don't want to try to push the truth into being reflected in the data exactly as you want it to be. You want to allow it to prove you wrong. To sum all of that up, getting an insignificant result is not a wrong result. It's just a statistically insignificant result. You don't want to look at it and say, oh no, I've made a mistake, I better change. That's bad. Lastly, and this is not so much to do with p-values or anything like that, but the idea that we have some sort of cutoff value is something that I don't particularly like. As I'll mention a couple of times in these videos, anytime in statistics that you choose a cutoff value, it's generally not really how statistics work. Statistics tends to work on sliding scales and mores and lesses, not yeses and nos in such a way. Anytime you have some sort of cutoff value, like a p-value of less than 0.05, you get really weird results. Like, for example, isn't it strange that a p-value of 0.049 is statistically significant, but a p-value of 0.051 is not, if you have an alpha level of 0.05? That's weird. That doesn't really reflect a real difference between the two, and yet we're making significantly different choices on the basis of them. That's sort of artificially induced by the fact that we have this cutoff value. And it doesn't even really matter what the cutoff value is. It's just the fact that we have one. Statistics doesn't really like cutoff values in that way. And so anytime you have them, things get weird. So while I've talked quite a bit about hypothesis testing, and I am going to continue to use it in these videos, I'd recommend that you think more carefully about just what is the precision of your estimate? What is your standard error? What does your confidence interval look like? That's going to give you a more nuanced view of what you can actually learn about the world based on the estimate that you have and a recognition of the sampling variation that you faced. It's going to do a better job of doing that than just worrying really a lot about whether you are above or below some cutoff value that you happen to arbitrarily pick. All right, that's my rant about it anyway. Thank you. See you in the next video.